me stop sharing.
Oh, good morning, good afternoon, good evening. So I'm pleased to chair this session. First, I'd like to thank Miguel, Irene, and Kumran for organizing this conference, and more broadly, keeping our community live and productive during the pandemic through the seminar series. So as Irene said, that there will be 3 talks, 30 minutes each, and after that we have time for Q&A. So the first speakers are actually 2 speakers, Timo Weigand and Daniel Klawer. So the title of their talk is Emergent Heterotic String, the Weak Gravity Conjecture and Quantum Corrections. 30 minutes, please start.
Okay, hi, so let me try to share my screen. I hope you can see it now. Okay, thanks again for organizing this workshop. It's a great pleasure to be sharing the first talk with Timo Weigand here. And yeah, I don't have to read the topic again. So we're talking about emergent heterotic strings. And these occur at infinite distance limits in the field space, for example, in F-theory compactification. And in the second part of the talk, I will then discuss how the weak gravity conjecture arises from geometry in this setting and how quantum corrections affect it. And then in the end, Timo will talk about how precisely we can get a handle on the weak gravity conjecture states using the elliptic genus. So as we all know, the distance conjecture postulates that at infinite distance in field space, we are greeted by an infinite tower of states, which becomes exponentially massless in the distance. And the emergent string conjecture states that the nature of the tower can be used to usefully classify these limits in the following way. The only thing that can happen is we either have a decompactification limit in which a KK tower dominates, or we can have an emergent string limit where the excitations of an emergent string, a critical string, dominate in the limit. And usually these strings arise from wrapping extended objects on shrinking cycles in the geometry. And this conjecture has been checked in many settings. For example, in F-theory compactifications on Calabi-Yau 3-folds to 6 dimensions, where we can tune the Kähler moduli to get a shrinking P1 on which we can then wrap a D3 brane, and this gives rise to a heterotic string. And also in type 2b string theory on a K3 surface, also to 6 dimensions, where again we can wrap a D3 brane now on an elliptic fiber. Type 2b on Calabi-Yau 3-folds has been also studied in literature, and very interestingly also in the hypermodular space, where different limits give rise to light F1, D1 strings, so these are quite familiar, and also D3 branes wrapped again on elliptic fiber, which give dual type 2 strings. Now, one setting that has been also studied is type 2a or M theory on a Calabi-Yau 3-fold, where again by tuning the Kähler moduli, one achieves shrinking of certain 4-dimensional fibers, and then one can wrap a 5 brane on it and get again a heterotic or type 2 string. And in the current setting, we are looking at F-theory compactified on a Calabi-Yau 4-fold, and there again the D3 brane is the important object which we want to wrap on a curve. In the setting, we have a 4D n equals to 1 theory, and we look at limits in the Kähler moduli base of the 3-dimensional base, which I call B3. And let me call the Kähler form J prime. And now a general infinite distance limit is a superposition of 2 things. So first of all, we can do a homogeneous rescaling of the Kähler form by a parameter mu on the left-hand side, which we then scale to infinity. So that's just a simple decompactification. And we can also, in case one of the Kähler cone generators, which I name J0 here, cubes to 0, scale the corresponding 2-cycle volume to infinity and adjust the other 2 cycles in such a way that the volume stays finite. So we have an infinite volume limit and a finite volume limit, and the general limit will be a superposition of this. Now the finite volume limits have been classified already in 2019 And a useful thing to do is to classify them into two subsets of limits. The first one is where the base admits a J0, which also already squares to 0. And the other class is where J0 does not square to 0. So let us focus for now on the first class of limits, the so-called J class A limits, where we have one Kähler-Kohn generator J0, which cubes to 0, but does not square to 0. So J0 squared is non-trivial. Now we want to group all of the other Kähler-Kohn generators according to the intersection properties with J0 squared. By assumption, this is non-vanishing. And if the intersection with one of the other Kähler-Kohn generators with this object is non-vanishing, then we'll put it in this index set, which I name I1. And if the intersection is vanishing, then I will put it into this index set I3. And then one can derive additional constraints on the intersection numbers. So in this setting, we can explicitly realize a limit where the volume stays finite by just scaling this generator by lambda. And these have to shrink accordingly because they intersect non-trivially with J0 squared. So if the I1 generator scale like 1 over lambda squared, then we arrive at a finite volume limit, which is non-trivial. Okay, so in this setting, we have a distinguished curve class C0, which is given by the square of J0, which by assumption was non-vanishing. And its volume goes to 0 in the limit. And for this curve, we really only have two options because the anticanonical divisor of B3 has to be effective. We either get a P1 fibration or a T2 fibration of the base B3 itself. So B3 is itself a fibration over another base B2. And the situation is depicted here on the right-hand side. And we want to focus on the P1 fibration because in this case, the D3 brane wrapped on C0 gives rise to an emergent heterotic string in 4 dimensions. So two problems have been noticed by us in this setting. First of all, you could envision a geometry which admits a limit where two P1 fibers shrink at the same rate, two different P1 fibers. So the trivial example, of course, where B3 is just P1 cubed, and then you can just shrink two of the P1s at the same rate and blow up the other one to stay at a finite volume. And in this case, naively, you get two heterotic strings which become light at the same rate, which sounds a bit crazy. And indeed, we can see that in this particular case, the KK tau dominates over the string tower. So this is actually a decompactification limit, and there is no meaningful way in which the two heterotic strings become light and relevant at the same time. And we prove that this is the case in general. So in this meaning, in this sense, the heterotic string is always unique. On the other hand, another potential problem that arises is that the constant volume limit generally leads to the fact that the KK scale decouples from the heterotic string. So if we just have these two Kähler-Kohn generators, which we scale as before, then we find that the base blows up like lambda squared, and the P1 fiber shrinks like 1 over lambda squared. So then you can just compute the ratio of the heterotic string mass scale and the KK mass scale associated to the blowing up of the base. And you will see that the KK tower decouples from the theory. So naively, you would think that somehow this leads to a critical heterotic string propagating in less than 10 dimensions, because there is no dual tower of states which appears in this limit. In the dual heterotic picture, the heterotic string will propagate on a Calabi-Yau threefold, which is elliptically fibered over the same base B2. This limit actually shrinks the base, and we will see, or we have seen in our paper, that alpha prime corrections obstruct these limits, and we need, in fact, also to superimpose this with the global rescaling of the Kähler form to get a consistent limit. So this is not the focus of today's talk, but you can find the story in our paper. And the upshot is that these limits can be classified in the following diagram, So again, we have these two parameters, mu and lambda. And for mu squared, scaling like lambda, we get a unique emergent string. So the uniqueness here is important. At the same scale as the KK tower from the base. Now we can also scale mu even faster than this here, which results in a decompactification. But on the other hand, we cannot scale mu slower, because in that case, we are hit by alpha prime corrections, and we are shrinking the base in the heterotic dual frame. Okay, so the focus now is the weak gravity conjecture in this setting. And as is familiar for everyone here, the weak gravity conjecture gives us an upper bound on the mass of charged particles in the following form on the right-hand side. And we can interpret this as being the condition for extremal black holes to decay, or as a repulsive force condition on test particles in the theory. How do we realize the weak gravity conjecture here? So suppose we have any divisor in the geometry which intersects non-trivially with our curve C0. Then this divisor will grow in the limit as mu squared lambda squared, so it goes to infinity. And if this S is wrapped by a 7-brane, our limit corresponds to a weak coupling limit for the gauge theory on the 7-brane. And in order to then prove the weak gravity conjecture, we need really two ingredients. On the first hand, on the one hand, we need the tower of states, where we need the charge to be bounded in terms of the excitation level of the string. And on the other hand, we need a relation on the geometry, which is that the volume of the curve C0 times the volume of the gauge divisor is roughly speaking the same as the volume of the three-dimensional base. So putting this together, we can show that there is a tower of excitations of the hydraulic string, which satisfies the weak gravity conjecture in 4 dimensions. Okay, it works as follows. We can write down the quantity q squared g squared. Now q squared is bounded in terms of the excitation level, so we can trade them. On the other hand, the Yang-Mills gauge coupling will be related to the divisor volume. Now, using the mass formula for the string excitations, we can trade the excitation level for the mass of the string state divided by the heterotic string tension. And the string tension, again, in our setup is given by the volume of the curve C0, because that's where we wrap the D3 brane. And now, using our formula on the right-hand side, we can replace this by the overall volume of the base. And this in turn gives us mk squared over m Planck squared. So if we can prove this and this, we get the weak gravity conjecture for the string states. So let's focus first on the geometry of the limit. A simple case is where we again only have the 2 Kähler generators, and we ignore the overall scaling mu because it drops out of the relation between the volumes. And we can make a general ansatz for the gauge divisor in terms of the Kähler generators. Then we can simply compute all the quantities that appear. So the intersection between C0 and S, can compute the volumes asymptotically. And we indeed find that the relation between the curve volume, the gauge divisor volume, and the volume of B3 is fulfilled up to corrections of order 1 over lambda cubed in the limit. And in fact, for J class A limits, which we focus on here, this was already proven in this paper, 1919. And in our paper, we also extended the proof to J class B limits where the fiber cannot be realized in terms of this square here. So this covers them all cases. Okay, we have just seen very briefly that this relation does receive corrections away from the strict limit, and additional corrections also arise from alpha prime corrections in F theory. And these corrections have been obtained, for example, by uplifting higher derivative corrections to M theory in 3 dimensions. And these corrections are given in terms of basically 2 quantities here, both of which can be written in terms of integrals of characteristic classes and Kähler generators. So the details are not very important here, but just keep in mind that these are suppressed by divisor volumes, these corrections relative to the classical value here. Now, first, we want to interpret these in light of the hydraulic F-theory duality. So since we have this vibration of B3, it's useful to think about the Kähler congenerators as being either sections of the vibration or vertical devices. In fact, we can also have blow-up devices, but we will ignore them here. So these can be then mapped onto the different Kähler congenerators with the different intersection properties as defined before. And the vertical devices map to Kähler moduli of the hydraulic string base B2 as follows, whereas one of the sections maps to the hydraulic dilaton. The parametric scaling is such that the vertical divisors go like mu squared over lambda, and the sections go like mu squared over lambda, mu squared times lambda squared. So by keeping track of the scaling with mu and lambda, we can distinguish between contributions which are suppressed by vertical divisors and sections, and hence suppression by the hydraulic dilaton or dependence on the hydraulic Kähler moduli. Now in our example, we had that the volume of B3 receives corrections at order 1 over lambda cubed. And in general, we see this, that the corrections from the geometry are of this order. So let us parameterize this as follows. So this quantity, which we need in order to prove the weak gravity conjecture, was 1 in the limit. But away from the limit, we get a deviation, which we call delta 0, and which goes like 1 over lambda cubed. And then we can decompose this as follows and see that this goes like the hydraulic Kähler moduli with a suppression by the hydraulic dilaton. In contrast, the alpha prime corrections have a different scaling, and we include them in terms of this correction delta 1 here, which goes like 1 over S hydraulic. Now we can explicitly map the corrections to the geometry to threshold corrections to the hydraulic gauge coupling. And the hydraulic gauge coupling receives a holomorphic contribution from the gauge kinetic function and also a non-holomorphic piece. And in F theory, the gauge coupling is just given by the volume of the divisor S. And then by running the F theory coupling to the hydraulic string scale, we can achieve a match between the two. So again, we parameterize this by delta 0 tilde and this by delta 1 tilde, such that roughly speaking, delta 0 tilde, the holomorphic piece, maps onto the geometric corrections in F theory away from the limit, whereas delta 1 tilde maps onto the alpha prime corrections in F theory. Now, the weak gravity conjecture relies on this condition, which receives corrections, which we have just seen to be hydraulic loop corrections. And now we can check what happens to the weak gravity conjecture, including these corrections. Without discussing black hole solutions, we can check the repulsive force condition, which can be seen to hold trivially in the infinite distance limit, in the strict limit. So this condition translates into this here in our setup, and imposing this to still hold, including the corrections away from the limit, we need that also the hydraulic string excitations receive corrections. So their masses also need to be corrected by this quantity delta, and then by imposing this inequality ring can relate delta to the corrections from geometry and the alpha prime corrections. And as a result, we find that if we want this to be still satisfied, this condition, then also the usual weak gravity conjecture relation, GQ M Planck over MK is bigger or equal than 1, has to be modified. And delta 0 and delta 1, we can give explicit corrections which are then model dependent. Okay, that concludes my discussion of the geometric aspects. And Timo will now discuss how the weak gravity conjectures states can be counted by the elliptic genus.
Okay. Hello, everybody. Also from me, big thank you for having us. You can see the screen? Yes, perfect. So in the remaining 5 minutes or so, I'd like to briefly discuss some recent results on the modularity properties of the elliptic genus of strings in 4 dimensions and how this ties in from the perspective of the weak gravity conjecture. So as we just heard, in order to prove this, the weak gravity conjecture in the present context, what we need to show is that there exists a tower of states in the excitation spectrum of the emergent 4-dimensional heterotic string, whose charge squared is proportional to the excitation level in the string excitation spectrum. So unfortunately, we don't have, of course, a fully explicit conformal field theory description in general for these emergent strings. There can be NS5 branes and other complications. But the solution is that in generic situations, I mean, for generic background fluxes, to be more precise, what suffices is only to exploit the modular properties of the 4-dimensional elliptic genus of the heterotic string. However, there are some recent surprises. Namely, the main point is that this elliptic genus takes value in the ring of quasi-Jacobi forms rather than Jacobi forms. And this, in fact, is important if we want to prove the sublattice weak gravity conjecture. So the elliptic genus of the string, as you all know, is an index partition function over a subsector of the string on a torus, the subsector with periodic boundary conditions. It is an index. We include a -1 to the f the fermion number. And we also keep track of the U1 charges of the string excitation. So in this way, we get a generating function for the degeneracies, n, which are essentially indices dependent on the excitation level and the charges. And this is what we want to gain information about. Now, the way we can approach the problem is by recalling how this emergent string actually came about. It comes from F-theory compactification, and we have a D3 brane inside a curve, which gives rise to the string. And this means that we can now use duality between F-theory, M-theory, and type 2 compactifications, all on the same Calabi-Yau fourfold, in order to relate in this way the elliptic genus to something that we can compute by mirror symmetry, namely the string topological string partition function. This works in close analogy to well-known results and established results in 6 dimensions, which to my knowledge go back to this early paper with lots of literature following. And the natural thing to conjecture, more precisely, is that the elliptic genus for this heterotic string, which we obtain as described, is encoded in the topological string partition function on the Calabi-Yau fourfold. More precisely, the degeneracies agree with the genus 0 chromophyton invariance of a certain curve inside the Calabi-Yau fourfold. And the curve in question is this. C0, that's the curve on which we wrap the D3 brane in F-theory to get the string. E tau is the full elliptic fiber. And C fib, this is just a curve in the fiber associated with charged states. And N and Q correspond in the elliptic genus to excitation level and charge. And now the important point is that on fourfolds, the computation of these chromophyton invariants depends crucially on the background flux, because we have F-theory on a Calabi-Yau fourfold, including fluxes. So the definition and computation of the chromophyton invariance is much more complicated, but it's still possible to do so, as is well known, by mirror symmetry on fourfolds. However, the fluxes for us determine the modular properties of the elliptic genus. And in fact, it turns out precisely the way we want it in order to get the sublattice weak gravity conjecture. So naively, we might have thought that the elliptic genus should have this modular behavior, more precisely that it should be a meromorphic Jacobi form of weight W equal -1. So in fact, in 6 dimensions, heterotic string in 6 dimensions, this is the case. In the perturbative heterotic string in 6 dimensions, it's a Jacobi form of weight -2. By this, we mean that it has good transformation behavior under modular transformations, but also under here these extra elliptic transformations with the weight. And here there's an anomalous prefactor, M, that's the elliptic index. It's related to the geometry. Details are not so important. If we had this, then we would be able to expand the elliptic genus in terms of this alphabet of 5 letters. The ring of Jacobi forms is generated by these famous bases or generating set of Jacobi forms. However, this simple assumption is not quite correct, fortunately. There are 2 types of anomalies, one of which is well known also in 6 dimensions from Calabi-Yau threefolds, and the other one is new or is tied to 4 dimensions. So the well-known anomaly is a modular anomaly, namely if the string whose elliptic genus we compute is itself a bound state of two strings and can decay into two strings, then the elliptic genus also includes the second Eisenstein form E2. And this is the case, for example, if the heterotic string can split into two E strings or many other types of possibilities. So in the presence of NS5 branes. And there's a good intuitive understanding why this leads to modular anomaly. More precisely, this second Eisenstein function doesn't quite transform like in a modular form of weight 2, but there's here this famous and well-known additional term. This is true for Calabi-Yau fourfolds as well, but the new piece on fourfolds is that in addition, there's an elliptic anomaly with no analog in threefold, and this depends on the flux. So the idea is that we have gauge flux. Gauge flux is described by a four form. The four form has, in F theory, has one leg along the fiber, and this background therefore destroys the modularity of the elliptic genus in a certain way. And the way how it destroys it means that we have to include also these E1s, which is kind of the analog of the Eisenstein function E2, and which in particular has a terrible anomaly also in the elliptic transformation property here. So this, in fact, can be made very precise and proven by applying the famous BCOV formalism of our chairman and of Qumran and collaborators from Calabi-Yau threefolds now to Calabi-Yau fourfolds. Here I'm only flashing the results. The details are not important. It would take too long to define all the objects, but we clearly see that there are two types of modular anomalies. The first modular anomaly, which is present also on threefolds, this implies this is there if we have a splitting of the string like on threefolds, but then the new thing is this elliptic anomaly equation, which is in general non-zero for generic fluxes. And in fact, it turns out the elliptic anomaly, or what appears on the right-hand side, looks something like something that comes from 6 dimensions. More precisely, what appears here on the right-hand side are the generating function for certain Chromafitten invariants of embedded threefolds inside this fourfold. So there's a rather rich geometric structure in here, which I cannot really go more into the detail of. The upshot, however, is that using this and various identities, one finds that the elliptic genus is in general written in this way in 4 dimensions. It is a sum of a modular form of weight -1, including also this E2 piece. This was the naively expected result. But in addition, there's something that involves the E1 piece. And this, in fact, can be written as a derivative of a -2 form. So this is something of 6-dimensional origin. And the point, this is why I'm telling you all this in this context, is that this second term here, this is responsible for the fact that indeed the sublattice weak gravity conjecture actually holds. Namely, we can look at the 2 contributions to the elliptic genus in turn. The first contribution, this is the one that we have naively from Z-1m. We can perform a theta function decomposition of this Jacobi form of weight -1, and it turns out that if we do so, that we find super extremal states, but they do not form a sublattice. They form only shifted sublattice, something that had been observed already a bit earlier. So we have a shifted sublattice of super extremal states, and naively you would think that this is at odds with the sublattice weak gravity conjecture. However, generically, for generic fluxes, we also have the second term. The second term here includes a sublattice of weak gravity conjecture states, namely a sublattice of coarseness 2m. M was the elliptic index, which is determined geometrically, and these are the famous states, which indeed then satisfy the weak gravity conjecture. So the sublattice weak gravity conjecture is satisfied because of this extra elliptic anomaly in 4 dimensions. Okay, so, oops, no, sorry. So to conclude, if we go back a bit from this technical exercise and ask ourselves, why does the weak gravity conjecture hold, or rather, when does it first of all hold, then the answer should be this. When does it hold? It holds asymptotically, as we expect, in the limit G-Young mills to 0. So it holds whenever we can take a limit G-Young mills to 0, which is not always the case. Why does it hold in this case, if we can take the limit G-Young mills to 0? because these limits are at infinite distance, and according to the conjecture, there are two possible types of such infinite distance limits, decompactification or emergent string. If it's a decompactification limit, then the gauge coupling which goes to 0 in the limit is the gauge coupling associated with the Kaluza-Klein U1. In this case, the weak gravity conjecture is the KK tower, as has been described in detail in this paper. And for example, in the 4D n=2 context, many dual and very intricate manifestations of this in a dual language, type 2B language, have been described in detail here, which prove the weak gravity conjecture for such types of limits. For the emergent string limit, the other possibility, we have both a string tower and a KK tower, as we heard before. If the gauge coupling we are interested in is the KK one, again, the weak gravity conjecture tower does the job. If not, then the G-Young-Mills, which goes to 0, is the one that is probed by this emergent tensional string. It's a heterotic string in that case, and the sublattice weak gravity conjecture holds because of the modularity properties of the string. So this would be the essence of what's going on in the most general situation. This is in the limit G-Young-Mills to 0, that works on the spot. And we try to see in the first part of the talk what happens is if G-Young-Mills, if we take into account quantum corrections, go a little bit away from the limit where G-Young-Mills equal to 0. And according to our proposal, there is a conspiration now of, on the one hand, the threshold corrections and mass renormalization terms in the string spectrum, so that the weak gravity conjecture still holds even away from the strict G-Young-Mills equal to 0 limit. Okay, thank you very much.
Thank you. So we have some time for questions and comments. You can raise. Oh, Tim, you have a question? You can unmute yourself, I think.
Okay, yes, sure. I just had a question for Daniel. So in very simple setups, like, so you discussed mostly lambda and mu go to infinity, but in very simple setups, if I just take string theory in flat space, I put it on a circle, there are two directions, right? You can run to infinite limit or 0 limit. In your more complicated setups, what do you know about this kind of opposite limit directions? Can those be understood or not?
You mean the limit where the volumes shrink to 0,
yes,
so to speak? Yeah. So we try to look at the limits which are where we can still kind of have some control, so we can get a perturbative handle on the corrections. But yeah, I don't think we can say much about the opposite direction. It's just not very well under control.
But you said you looked at some limits and there you find essentially the same, or?
So we have looked at limits where we shrink cycles in the geometry. So in our case, that was the curve C0. And now, if I understand your question correctly, you're asking what happens if we shrink also the base of the vibration. Is that what you're asking?
Yeah, I mean, I'm just wondering, if you shrink anything, do you always lose control, or do you sometimes also find some kind of emergent string or some kind of dual string theory or something, or you just don't know?
Yeah, so these would be the limits in which the KK tower decouples then, and yeah, we're not really in a setting where we know what happens. So if we can just get rid of the extra dimensions, of course, then we are left with a heterotic string propagating in less than 10 dimensions, and yeah, we don't really know what to make out of this. If there's a dual tower like a KK tower, if we have enough supersymmetry, of course, then we cannot get rid of the extra dimensions. We just go to a different duality frame, but that's not what happens here.
Mm-hmm.
Okay, so Kumran is raising hand. So
yes,
you can unmute.
Yes, thank you. Very nice talk. I have a question. So am I understanding correctly that if you use the cosine modularity and so forth, the Jacobi forms, basically, doesn't it boil down simply to the character of U1 level K? Am I missing something? Could you just say that since we have a U1, in other words, your machinery is more general, it seems, but the weak gravity conjecture part of it, doesn't it just boil down to the statement that there's a theta function, which is the character of the U1 level K?
Exactly.
Ah.
That's exactly what it boils down to. And the point here was to show that this holds also in situations where, for example, you have NS5 branes in the background, or where you don't have full control of the CFT as such. I mean,
I see. So that's why you're doing this. I see.
Exactly. But in 4 dimensions, I mean, in 4 dimensions, naively, one might think that there is this problem of the shifted letters because the weight is a -1 letters is -1, and the functions, these weak Jacobi functions, they are antisymmetric, and hence we didn't actually find the states that we need, but these are provided precisely in the right dimension by these extra states which come from this extra anomaly, which is not present in cases where it's not needed. But at the end of the day, it's precisely what you say, yes.
Okay, thank you.
Miguel? Miguel, yep.
Yeah, thanks. Very nice talk. So Timo, probably you explained this at some point, but I just didn't get it. So because you're looking at the elliptic genus, but at the same time you're imposing there is a small coupling. I thought that with elliptic genus you could just kind of like, I mean, you didn't need to do it at weak coupling, right?
No, we don't need to, but that is the situation where we have the emergent string to start with. So the reason, on the last slide, I said we need the weak gravity conjecture, of course, in the limit g equals to 0, as everybody would have expected. And the reason is not that this is the only limit where we can use the elliptic genus, but this is the limit where we have a string to start with.
Right.
And then, of course, where we need the limit g equals to 0 is that if then we can trust the mass formula for the string states. I mean, the relation that m squared of the string states is proportional to n is of course perturbative. And in fact, we claim that there will be renormalization effects, and there must be, because GL-Mills, which also appears in the weak gravity relation, of course, also gets threshold corrections. So yeah, but the elliptic genus as such, of course, can be computed wherever you are in moduli space.
Okay, thanks.
Irene?
Yes, thank you. Thank you for the talks. Just something very quick. I think in the first part of Daniel, it was not very clear to me when you were discussing the repulsive force conjecture, whether you were assuming that the conjecture works and then guessing some of the corrections, or computing all the corrections and then checking that the conjecture works, or how was it?
Yes, thanks for the question. Sorry, I would have included an example if there was more time. But yeah, in fact, we do check that it holds in the strict limit. And then what we impose is that, so that's for vanishing gauge coupling. And we impose that it should still hold for finite gauge coupling. So a very weak coupling, but not strictly zero coupling.
Okay, so you don't check it, you impose it and then derive things from that.
No, we don't impose it. We can actually check it explicitly in the limit.
Okay, but
so
not for the corrections. Yeah.
In the strict limit, it does hold, we can check it. And then we impose that it still holds after including the subleading corrections. That's the logic.
Mm-hmm.
And if I may add, so one makes an ansatz for the masses of the states for the renormalization effects. And what we show is that there is a consistent ansatz such that the weak gravity conjecture in the end holds. And this is where the repulsive force condition by Aran and Rodelius et al. Comes in, because the masses appear on both sides of the weak gravity conjecture relation. Hence, a consistent ansatz can be made. So this could have gone wrong.
Mm-hmm. Okay, thanks.
Okay. Any other question, comment? Oh yes, Naomi, you have your raising hand, so please.
Yeah, just a follow up to that question, actually. So away from the limit where you impose the weak gravity conjecture and you have the corrections delta 0 and delta 1, does that then tell you, like, what in general does that tell you about the alpha prime corrections and the geometric corrections? Does it tell you anything interesting, or is it something that you just have to check case by case?
Yeah, thanks for the question. Again, that's a very important point. We actually, regarding the alpha prime corrections in our paper, we actually find one contribution, which is not completely fixed by the classical uplift from M theory to F theory, and which does not have a clear heterotic interpretation. So yeah, if we want to have the heterotic string F theory reality, this term should actually vanish. And this term was not determined in the literature. So we actually get a condition from consistency of the duality to the heterotic string. And yeah, but for the deltas, we don't really get another constraint besides that. So most of the corrections are fixed by the geometry. If we just fix a model, a concrete model, then the deltas are basically fixed up to this subtlety. And then we can determine the corrections to the string excitation masses from that.
Thank you.
Okay. Any other questions? Okay, so timing is perfect. So thank you for the first speaker, Timo and Daniel, for the beautiful presentation. And